Well, let's look at some of this homework here. So this would be chapters 11 and 12. So on this first one here, we want to find the head loss between the two pressure gauges there. We got 40 psi at A, and we want to figure out what it is at B. Okay, and this is going to be a Darcy-Weisbach one, so it's a little bit more involved perhaps than the Hazen-Williams. All right, so what we got here, we got the flow is 400 gallons per minute, and the temperature is 70 degrees. And we've got the pipe size is 8 inches. So we take the 8 inches, divide it by 12, you get feet, because that's how you want to look at pipe sizes in this Darcy-Weisbach method. So that'd be 0.667 feet. All right, now what I would do next would be to find the velocity, because I'll need that also. So I'd go ahead and look at the Hazen-Williams chart to get that figured out. And so that is one thing to remember on this stuff, is that you don't need to be doing that Q over VA stuff all the time. Now, sometimes you might need to do it, but for some of this stuff, you don't. So because if you've got standard pipe sizes and a standard flow, you can just find this on the chart. Okay, so if we've got an 8-inch pipe and the flow is 400 gallons per minute, we can go ahead and find the velocity, and it looks a lot like 2.55 until my screen just blew up on me there, but here we go. So 2.55. So that's the velocity. Okay, so the velocity here will be 2.55 feet per second. All right, so that's what we start off with there. Now we've got 70 degrees, so you need some information to kind of look at turbulence versus laminar flow and get onto that chart to find some friction factors and all that. So let's have a look. So we got 70 degrees. So if we look at the chart, which is in the book towards the beginning, it's in chapter 1, I think. It's on page 58. If you look at 70 degrees, you get the density. It's 1.936. And that's slug per cubic foot. The slug is kind of an odd unit. It's the English system that we use here in America, or imperial system as it's called sometimes. And that's the unit of mass. So it's slug per cubic foot. And then also we've got the viscosity there that we need. The viscosity is like how sticky the fluid is. Honey is viscous, much more viscous than water. So viscosity is kind of how thick and sticky a fluid is. So what we get for viscosity then, so the viscosity is 4 zeros, so 0.12340 And that has some rather funny units, pounds second per square foot, okay? And what that is, if you look at the variable on that, it's called mu. It's a Greek letter that's used for viscosity, okay? All right, so that's kind of our starting point, is that information. Now what we want to do is find something called the Reynolds number. So the Reynolds number is the pipe diameter times the velocity times the density, that's rho, that's like another Greek letter, divided by the viscosity, okay? And so if you have everything in standard units, you don't need to be worrying so much about units, but it'll all kind of come out. Okay, so 0.667 feet, the velocity is 2.55 feet per second. We've got 1.936 slugs per cubic foot. And then we can divide that by mu, which is 4 zeros, so 1, 2, 3, 4, 203, and that's pounds second per square foot. And I think if we look at those units, they'll pretty much cancel. Anyway, I hope. All All right, so what we end up with, although there is that pound and slug thing, the units will work out. Let's just kind of leave it at that. Okay, let's not worry about the units so much on this. What this comes up with is a dimensionless number, 162,209. That's a number that has no dimensions. It's called the Reynolds number, and that's a number that doesn't have any dimensions. Okay. Now, we usually like to get that into scientific notation, so that's 1.62 times 10 to the 5th. Now, I'm getting 10 to the 5th by kind of counting the decimal place over. 1, 2, 3, 4, 5. So that's 1.62 times 10 to the 5th is what that is. All right, so there we go. All right, now what we want to do here is we want to go to this head loss or friction factor chart is where we want to go. So we have to have a look at that. Okay. And that is also in your book. It's at the end of chapter 11, and it's kind of, I'll have to get to it first and we'll find the page. There it is, okay? It's on page 120. Okay. All right, now we want to use this for the information we've got. Now, one thing we need here is the average depth of an imperfection in the pipe. That's called epsilon. And we have uncoated cast iron, so it's 0.0008. That's our value of what's called epsilon. What that is the average imperfection in the wall of the pipe. So pulling off of that chart there, I get epsilon, and that's 0.0008. Okay. Now what we look at on that chart is a ratio of the biggest imperfection in the pipe divided by the pipe diameter. These numbers are all in feet, so this will be another dimensionless number. So it's 0.0008 divided by 0.667. So what that'll get you is 0.0012. All right, so what we got now is we've got the Reynolds number and we've got this epsilon over D ratio. Okay, so once you have that, you can go onto the chart and find the friction factor. So that's the reason that we're doing all this stuff, is to get to the friction factor. All right. All right, so we got the velocity, and at the temperature, we got the density and viscosity, we got the pipe diameter in feet. 8-inch pipe is 0.667 feet diameter. We plug all that in and get the Reynolds number, 1.62 times 10 to the 5th. We also look on that chart and get the epsilon value, which is the average bump or pit in the pipe divided by the pipe diameter. Okay, we got all that stuff. And now what we can do is we can figure out this friction factor. Okay. So we'll come here, and what we're going to do is have a look here. I think we're going to try and clean this up a little bit. Like that. There we go. All right. All right, so our epsilon over D is 0.0012 is what that is. So here's 0.0016 right there. So this is going to call for a little bit of kind of interpolation, kind of guesstimation sort of thing. Here's 0.0005. So 0.0012 on this scale ought to be pretty close to the 0.0016, I would think. So I will take that line and draw a parallel to that curved line across. Okay, so that curved line's starting to go up a little bit. It's hard for me to draw on this screen and do a great job, but something like that. All right. Now I've also got that Reynolds number, and the Reynolds number is 1.62 times 10 to the 5th. So that's right about in here. Here's 10 to the 5th. There's 1.5 times 10 to the 5th. There's 2 times 10 to the 5th. So I'll pick that number up and intersect. I'm going to find the intersection of these 2 points, and then I'm going to take that directly to the right. Okay, and that's how I get that friction factor. And I estimated that at about 0.022. You might have got 0.021, you know, I don't know. It's just a read off of a chart, so we're not going to get too worked up over that, all right? So just do the best you can with that. So we good with that? All right. Okay, so that's a lot of work to get that number, but once you have it, you've got pretty much all the information you need to find the head loss using this Darcy-Weisbach method. Okay, so the friction factor F right there is 0.022. Okay. So once you've got that, okay, what we can do is plug this into this whole head loss formula, which is F L V squared over D and 2G on the bottom. All right, and that's how we can find the head loss. So what I'm going to do is take the 0.022 times the 3,000 foot length of the pipe times the velocity squared. And I'm going to divide that by the pipe diameter in feet. So that's 0.667. Kind of didn't write that very well. Let's try that again. So 0.667 feet divided by 2 and divided by the acceleration due to gravity, which is 32.2 feet per second squared. So there we go. So when I run those numbers, I get about 10 feet. I got 9.99 feet. So that's going to be the head loss. Okay? Whoop, not feet squared, just feet. There we go. All right, so that gets us to how much head loss we're going to have. Now, once we've got that, we can figure out what the pressure will be at point B. Okay, now what we got at point A is we got 40 psi, and we got 2.31 feet per psi. And so that will get us the pressure head there. It's 92.4 feet. Okay, so that's the pressure head at A. So if we kind of walk through this then, okay, what we can do is we can put a chart together. Now there's a couple ways to figure this one out. If we want to do it the way we've been doing it, we go in and build a chart. All right, so what we're going to have here is A and B, and then we'll have the head loss in between. We're going to have the elevation, the pressure head, the velocity head, and then the total. All right, now that's a flat pipe, so the elevations don't change, so we can call them both 0. The velocity head will be the same in that pipe. It looks to be a constant diameter pipe. If we're pushing the flow through a constant diameter pipe, the velocity is not going to change. So we can just leave that, just not even deal with it, and we'll be fine with that. Okay, we got 92.4 feet of energy at A on account of that pressure head, which is 92.4 feet. The head loss is 9.9 feet, and that will get us 82.41 feet here of total energy at B. Okay. Now there's no elevation at B, there's no velocity head that we're worrying about at B, so all of that energy will go into pressure head. So to find the pressure at B, we can take 82.41 feet and just convert it into pressure. 0.433 psi per foot, and that'll get us the pressure, which is 35.7 psi. So that's how I would set this up using the methods that we've been using. if you wanted to shortcut this method a little bit, you could on this one. You could notice a few things, primarily that the pipe is flat and constant diameter, so you don't have to worry about elevation head because the pipe is laid flat. You don't have to worry about velocity because it's got a constant diameter, so you could just work with the pressures. So maybe a little quicker way to do this, if you wished, would be to look at the head loss as 9.99 feet. Convert that right into pressure. 0.433 psi per foot. And that comes out to be a drop in pressure that actually is about 4.33 psi. So if you don't want to go through the whole bit with the table, you can just realize that you're starting at 40 psi and you're going to drop by 10 feet of pressure head, which is 4.33 psi, and that would get you the pressure also, 35.7 psi. A little quicker way there on the bottom. Normally I like to set those tables up, but on this one, it's a pretty straightforward problem without the table, so I just want to, you could do it that way too if you wished. All right, whatever way you're comfortable with, I think is fine. So are we doing all right with that one? We got any questions on that? All right, so that's the first one there. And that's the only one we'll do doing Darcy-Weisbach. I just wanted to get one in there just to get you a little bit of practice with that. Right? As I've said, if you're doing stuff by hand, the normal way to do this stuff by hand is to do it with the charts and the Hazen-Williams stuff. Darcy-Weisbach is more accurate, but it's also obviously a lot more work to do it, and that work may not be worth it given what what you might be trying to accomplish. So quite often we use the Hazen-Williams and the charts to do this stuff rather than doing this full-born Darcy-Weisbach method. So let's look at the Hazen-Williams and the charts a little bit here. Let's see what we got. All right, so let's look at the Hazen-Williams ones then. All right, now have a look in Moodle. I mean, I didn't assign all of them, so be aware that they're not, I didn't assign the entire chapter's worth of stuff. So be aware of that, okay? Okay, I did assign 2, 3, and 4. And those are just finding head losses, just some practice problems to find head losses. You've got the answers to those, so I don't really see the need to go through them unless there's questions or anything. We're doing all right. Yeah, those are, and that is something, you just use the chart and factor it up for the length of your pipe. Okay, now we do have some then that have C not equal to 100. And that's something we might have to deal with. We also have some of these other types of problems that can come up. So why don't we look at those? And that's 11, 6, and 7. Okay, so let's just get a feeling for how to work through these ones. All right. So if we got C100, 352 feet, and the head loss is 30 feet, what is the flow through the pipe? What you do is you work through the head loss. Okay, that's how you'd figure this out. So you've got 30 feet of head loss, and you've got 352 feet of pipe. So that's 3.52 100-foot lengths. So what we're going to do then is we're going to look at the head loss per 100, and that's 8.52 feet. That is the head loss per 100 feet of pipe. All right. Now what I would do next is I would go to the charts and start looking at this. We've got a 6-inch pipe, and we've got a head loss of 8.52 feet per 100, so we want to have a look at that. So now we're doing the Hazen-Williams method, so we want to get to the chart. There it is. Okay, so let's have a look here. So we got 6-inch pipe, and we have a head loss of 8.52. So for 6-inch pipe now, I'm looking for a head loss of 8.52. So I'm right in here somewhere. Somewhere between 800 and 850 is where I'm at. All right. So what you could do here on this one is say, okay, 800 gallons per minute for 6-inch pipe. What that has is 7.92 feet. And 850 gallons per minute has 8.86 feet. Okay. Now I got 8.52. I'm pretty close to halfway between the two. Now if I really want to get an accurate answer, I can interpolate that, but I don't see the need in this class to do that. These numbers are pretty general anyway. They're not pinpoint accurate. So I think if you said 825 gallons on that, because you're kind of midway between 800 and 850, whoops, I would call that good, okay? So that'd be gallons per minute, all right? And we're looking at the head loss per 100 and seeing what values of flow fit that, okay? All right, now the next one here, we've got 720 feet of pipe, 50 feet of allowable head loss. So we got 50 feet, and then we've got 720 feet of pipe. So if I take 50 feet over the number of 100-foot lengths, which is 7.2, I get 6.94 feet per 100 feet. All right, now that is the maximum head loss that I can have, all right? So what I want to do is see what sizes of pipe don't exceed that, all right? And so once again, we're going to go looking at the pipe table. And this time we're going to look for a given flow. The flow is 600 gallons per minute. So what I would do on this is I would go to the pipe table there, right there. And I'm going to start looking for 600 gallons per minute for different sizes of pipe, all right? There's 4-inch, and it's quite large. It's 33.45, so that's an awful lot of head loss, and it's a lot more than what I can deal with here. I can deal with 6.94, so that's not going to work. I can look at 6-inch, and there we go. That's 4.65. So what I just did was got a value above my maximum allowable and a value below. So I've got it bracketed, you might say. So what I would do next here is have a look at my situation here, and my situation here is 4-inch pipe. This is all based on 600 gallons per minute. 4-inch pipe is 33.45, and 6-inch pipe is 4.65 feet. Okay. I'm at 6.94. I'm in between those two. Now, if I've got a limit of 50 feet of head loss, I can't go any higher than that. So what I want to do is pick a value of pipe that is either 6.94 or lower. So I'll go with 6-inch pipe. That's the next size up that has 4.65. So if I go with 6-inch pipe, I'm not going to have more than 50 feet of head loss. Of course, if I go to 4-inch pipe, I will, and that will be a problem. Okay. All right. Now the next ones are when C is not 100. So there's a formula for that. And this is on your formula sheet. And what that formula says is the equivalent flow, Q, EQ meaning equivalent, is the actual flow times 100 over C. All right. So that's how you work out the fact that you may not have C100. We have a C100 table, but for this problem right here, we've got C130. So what I would do when I go to the table, on the table I need to use what I call the equivalent flow. All right, so that'll be the actual flow, which is 780 gallons per minute. And then I'll multiply that by 100 over C, which is 130. Now what's going to happen is I'm going to get an equivalent flow of 600 gallons per minute. So what the deal is if I put 780 gallons per minute through a smoother pipe, I'm going to have less head loss than I would pushing it through the C100 pipe. C130 pipe is smoother than C100. So when I put that 780 gallons per minute through that 10-inch pipe, I'm going to have less head loss for C130 than I would for C100. Okay? And I'm saying this because that helps you to remember how to build this fraction. See, I'm going to use the C100 table, but I'm going to do it for less flow. That way I'll have less head loss. So I want to set up this ratio or this fraction, whatever you want to call it, to make the 780 less, because I want less head loss is what I want. Okay, so for 10-inch pipe, C100 here, 600 gallons per minute now, not 780. See, I'm not doing 780 anymore because I'm adjusting for that smoother pipe. I'm going to use 600 gallons per minute. The head loss is 0.39 feet per 100 feet. Okay? So now when I've got that, I can take that 0.39 feet per 100, and then I've got 245 feet, so that's 2.45 100-foot lengths. So when I multiply those together, I get 0.96 feet. So we all right with that?
Yeah.
Good. Okay. Good deal. The other one's quite similar. The other one, the flow goes up because it's a rougher pipe. Okay. Okay. Then we get into these ones that are on the tables, and these are a lot like what we did before. So we've got these things. All right. So what you want to do is start building a table for these and working through that. You're going to find the head loss off of the charts and use that on the table. Other than that, that's just the new thing that's happening here. These are very similar to the ones you did in the previous chapter. They're building these energy tables. So for instance, on this one, you got 430 for the elevation of the reservoir, no pressure head. We're going to ignore velocity head. That's gone. We're going to get a total energy of 430. And then you're going to look at the head loss, 1,500 gallons per minute, 8-inch pipe. Okay, now that's 6.25 feet per 100 feet. For that condition, you can get that off the table, 1,500 gallons per minute through 8-inch pipe. And now we got 8.7 100-foot lengths. So you factor that up and you get 54.38 feet. So that's head loss, so that's subtracted. So the energy you're going to have left over is 375.62. Okay. Now the hydrant is at 310. So if you take 375.62, subtract off the 310, what you get is 65.62 feet. That's the energy you've got left over for pressure at the hydrant. Okay. So you can take the 65.62 feet and then just convert it back into pressure. Okay, so the things that we use on the table are in feet. If you want an actual pressure, you got to convert it back. So that's 28.4 psi. So that would be the pressure in the hydrant. So we're doing all right with that? Okay. All right, now the next one is, similar type of problem. It's a little bit more involved because you've got pressure here. So what you're going to do, you're going to get 212, 180.18, which might be a little bit overkill on the number of figures there, but that's fine. 180, something like that is what you want. So you're going to get 392. You're going to find the head loss, which ought to be 28.37 when you get it. That'll get you 363.81. Okay. The elevation here is 281. We're ignoring velocity head, so we'll get to the energy here, 82.81, and then convert that into pressure, and that's 35.9 psi. So that's, a similar type problem, just you don't have the open reservoir on that one. You've got a closed pipe with pressure gauges on it. So we good with that one?
Yep.
Good, all right? Okay. Okay, pump station there, 80 psi. Okay, now this one is one of those deals where we're going to have to find the flow on this one. Okay. So 80 psi, so you're going to got 300 feet of elevation. You've got 184.8, which is 80 psi expressed in feet. We're going to ignore velocity head. We're going to get 44.8. All right. Now on the other side, you've got the elevation there is 410.5. The pressure head is the required pressure head. That's 20 psi. And pressure head, that's 46.2. So on this one, I know what's happening at the second point also. The total energy there is 456.7. Okay. So I've got a total energy at A of 484.8, and I've got a required energy at B at 456.7, so I can find the difference between them. I total up both sides, and then I can find the difference between them. It's 28.1 feet. So that's the head loss you can have and still keep this 20 psi residual. Okay, so you can take that 28.1 feet and divide it by the number of 100 foot lengths, 3.52 100-foot lengths, and that comes out to be 7.98 feet per 100 feet. So that's the allowable head loss. Okay. So then you look at the charts. All right, so if you've got 6-inch pipe, C100, if you look at the charts for 800 gallons per minute, you've got 7.92, and for 850 gallons per minute, for head loss, you've got 8.86. Well, that's close enough right there. I think you could call that 800 gallons per minute. Okay. So what we're doing there is we're looking at the allowable head loss that can occur. So you doing all right with that?
Yeah.
Okay. All right. Okay, the next one, same sort of deal here, 300. The pressure there is 70 psi. Well, that's equal to 161.7 feet. Just multiply that by 2.31. We're not going to deal with velocity head here. Add them up, we get 461.7. Same stuff here that we kind of like what we had before, 365.5, a little different elevation. But the 20 psi residual, that's 46.2 psi, or feet, I'm sorry, feet. So we convert that psi residual into feet, 46.2, we add those up together. And then what we're going to find is what the requirement is at the house. And that's 411.7. Okay? So the difference is 50. So what that means, starting at this tank and pump station, you can have 50 feet of head loss, and you'll get 411.7 feet of energy at the house. And given the elevation, that will leave enough pressure head to get 20 psi residual. So once again, what you do is you take 50 feet and you divide it by the number of 100-foot lengths, which is 7.2, and that will get you 6.94 feet per 100. All right, and then we need 600 gallons per minute. We look at the pipe sizes, 4-inch, what we've got is 33.45. Now that's obviously too much head loss. 6 inch is 4.65. Okay, so the 6.94 fits between those, so 6-inch pipe will work. Okay. Okay, the next one here. Did you? Okay. Let's have a look then. All right, now there's no elevation here, so we got 0 and 0. We're not going to deal with velocity head. Okay, now the pressure head here, if we multiply this up by 2.31 feet per psi, we'll get the pressure head. For 32 psi, it's 73.92. So that goes here. Okay. Now 30 psi times 2.31 feet per psi, that comes out to be 69.3 feet. So that goes here. All right. So what we got here at A, we got a total energy of 73.92. At B, we've got a total energy required of 69.3. So we want to find the difference, and it's not much, it's just 4.62. Okay. So that's the allowable head loss, is what that is. So if we take 4.62, that's the allowable head loss. We got 1359. If we divide that by 13.59, we get 0.34. That is the allowable head loss per 100. Okay. All right, now we want to go look on the chart. And when we do that, we've got 12-inch pipe. So we want to go look at 12-inch pipe and an allowable head loss of 0.34. And we want to see how much flow we can get through this thing. So if we do that, 12-inch pipe, 0.34 head loss, right here. 900 gallons per minute. Right? What size pipe? Are we on 4-inch pipe on this? We're doing 4-inch, aren't we? Yeah. I got a typo in my book. Sorry. Okay, so it's 4-inch pipe. There we go. So 0.34. It's 50 gallons per minute.
Yeah, that's why I have it.
Yeah.
50 gallons per minute, and then I multiply it by 1.4.
Yeah, right. It should be 70 gallons per minute. Yeah. Okay. All right. All right. Okay, so I just had a bad pipe size there. Did I have a bad answer in Moodle? Or, okay, probably not. I had like kind of a little correction on my paper here, but I think we're doing okay. So we've got, so for C100, what we end up with there is 50 gallons per minute. That's the equivalent flow is what that is. Okay, but we've got a higher C. We've got C140. We'll get more flow through that pipe. So if I take the 50 gallons per minute and multiply it by C over 100, I'll get the actual flow. Because that smoother pipe, I can get more flow through it for that given head loss. I can get 700 gallons per minute through it. So if you want to look at the formula on that, it's the equivalent flow is the actual flow divided by 100 over C, or excuse me, multiplied by 100 over C. So if I want to find the actual flow, which is what I'm after there, that would be the equivalent flow times C over 100 is what I would do. Okay? That's what I'm doing down below there. Okay. And then on the last one there, it's a similar deal. Okay, so 307.2 for the elevation at the reservoir. So 307.2 at the hydrant, we've got 240. The required residual is 46.2, so that's 286.2. We want the difference between those, and it's 21 flat. Okay. So if we take the 21 feet of head loss and divide it by 5.74, what we get is 3.66 feet per 100 feet. Okay. All right, now we want to see what pipe size we've got, but we got C150. To go to the chart, we want to use the equivalent flow, which is the actual flow times 100 over C. Okay, the actual flow is 2,100 gallons per minute. Multiply that by 100 over 150, and you'll get the equivalent flow that we'll use on the table, and that's 1,400 gallons per minute. Okay. And then if you go to the table for 8-inch pipe, we got 5.5. And for 10-inch pipe, we got 1.86. That's the head loss for different pipe sizes for 1,400 gallons per minute. Okay, our allowable is 3.66. So we're in between these two. So you go with the bigger pipe, 10-inch. Is that good? Do you have those minor loss ones okay? You okay with those?
Yeah.
Okay. All right. So that's the deal there, okay? All right.